everyone and welcome back to Exam Ignite YouTube channel. This is 5th semester's digital communication subject of subject code BEC503, module 4, that is about error control coding, linear block code and the cyclic codes. So in this part 1 and part 2 videos, we'll be discussing completely. Here I have referred the model question paper and June-July 2025 paper and December-Jan 2025 paper to mark some of the important things that you need to know in this module. Firstly, the error control coding. In this, the error control coding using the forward error detection. This is a general explanation using the block diagram. This is important, and they have asked the advantages, disadvantages, then block code versus conventional code in one of the paper. Next, coming to the linear block codes, here we are having definition, matrix description, then syndrome and its properties, minimum distance consideration, syndrome decoding procedure that was asked in one paper, then Hamming codes. So basically this module 4, it is a problematic and you can expect more problems and numericals compared to theory questions. So but we will read some of the theory also, because sometimes they may ask you about writing the procedures or some of the theory points also. And then comes the cyclic codes, where you have the properties, then generator, that you see they have asked about to explain the generator block diagram and parity check polynomial along with the syndrome equation and listing the properties. So we need that. Then comes encoding, then syndrome computation and some of the examples. This is what we will be studying completely in this module 4. So starting with the first one, that is forward error coding. So it is a technique that is used to detect and correct the errors. It is detecting and correcting in the transmitted data without without requiring the retransmission. Retransmission is not required. Like you can say, like sending extra data with your data. You will send some extra along with your data so that receiver can fix an error that might occur during the transmission. So that if some error occurs, they can fix out of that. Next is adding redundancy. In this part, we are having two types. We can use this encoding method. One is by adding redundancy. When sending the data, we add some extra bits, that is called as the redundant bits, to the original message. These bits are actually not the part of the actual information or the original message that we are conveying, but they help to detect and fix the errors. Just we are adding some extra bits. Next, you can say like sending a backup plan along with the data that you are transmitting. Next comes error detection and correction. Here at the receiver end, you are having some extra bits. So these are used to check for the errors in the received data. And if possible, you can correct them also. At the receiver, this does not need to ask the sender to resend the data. This is one of the major plus point in this. So this saves the time in the noisy communication system. Next, in the block diagram, you can observe the first one is figure A and figure B. Here, discrete source, we are having channel encoder, and that is sent to the modulator. And from there, we send it to the waveform. And we are having detector and finally channel decoder and user. This complete part is known as the discrete channel, modulator, waveform, and detector. So another one simplified way can be written as discrete sources given. Here we are having encoder or the modulator. These two are combined. Then it sends to the waveform channel. Then comes to the again these two are combined. Detector or decoder, finally the user. This is figure 1 and figure 2. Here you can say figure 1 is a simplified model of the digital communication system. Coding and modulation are performed separately. Coding is done and then modulation. But here both are combined. This is the difference. Next, coming to the steps involved in this forward error correction is, first step, what happens? Encoding is done. This is our first step. Your sender will take the original data, that is a message bits, and uses an encoding algorithm to what? To add the redundant bits. For example, my message that I am transmitting is 1010. For this, I am adding this 110 has some extra bits. These are added. Then transmission. So here encoded message is sent over the communication or the discrete channel like the satellite link or the noisy phone line. You will send this data. This data is sent. After that, it is received at the receiver. Here it gets the message, but it receives with the errors due to the noise. So what happens here? Some are flipped. You can observe the sent data was 1010 and then 110. Here it has become 010. So decoder uses the redundant bits and detects the correct errors, and it detects and it corrects that error, so you will get the received original message. So this is how you have to prove that you have got the original message back. So thus this completes the error control using the forward error correction. So next we will move on to the linear block code. So what is linear block code? It is a code is said to be linear if two code words in the code can be added in the modulo 2 arithmetic to produce a third code word in the code. Modulo 2 arithmetic means modulo 2 addition happens like if you have 0 and 0 you get as 0, 0 1 you will get as 1, 0 1 0 you get as 1, and if you have 1 1 you will get as 0. This is the modular addition. I'm talking about the addition, modulo 2 addition. Similarly, arithmetic we are having multiplication, division and all, but we will be using the addition majorly in this segment. So an n comma k linear block code means they will specify in the question as n comma k. What is this n comma k? K is the number of message bits and n is the number of code word bits. So n minus k means it is a parity check. Parity check is nothing but the redundant bits that are there in the code. So how to find out the code rate then? Code rate is given by k by n. So systematic linear block code means here systematic refers to the message bit appears unchanged in the code word, and that is like code word either it will look like parity bit, message bit, you have to make it as dotted line here in the matrix, or message bit and a parity bit. This is how you represent it. So in the message block you have the symbol notation has m will represent from m0 to mk minus 1. C for the code word from c0 to cn minus 1. And from parity checked is b from b0 to bn minus k minus 1. So considering this as equation 4, 5 and 6. So next comes structure of the systematic code word. So now you have to represent it. So ci is given as bi, parity check bit and the message bit. So let us consider this as equation 1. So the first n minus k bits is called as a parity bits and the last k bits are the message bits which is unchanged. Then what is parity bit? From that time we are saying what is that parity bit? Each parity bit is a linear modular 2 combination of the message bits. That is, it is bi can be represented as pi, p0 I and m0. So this is how we write a pi. All the arithmetic is modular 2 coefficient of pi and Pij. So from this one equation that we have written and from the two we can write Pij is 1 to 0. If Bi depends on Mi it is 1, otherwise it is 0. So we use XORs of selected message bits. So all parity equation collapse into one matrix equation that is called as B is equal to M into P. This is an important equation that you have to note, where P is given by K into N minus K binary matrix, where the entries are 0 and 1. So next is from the equation 4 and 5 that we had written, we can write C is equal to B and M. So C is equal to B, substitute it as M into P, that is MPM. Next, you can also take the PM has common out here and that becomes M becomes IK. This is identity matrix. So here P is given by this type of matrix and I is the identity matrix. So you can write generator matrix has P into IK. So that is what we have given here. G is given by the generator matrix is given by K into N, where it multiplies 1 into K message bits and produces a 1 into K code bit. So C is equal to M into G. For a linear, what you can say is message bits will be 2. One is MI and MJ. Code words will be CI and CJ. So if you add them in the modular 2 addition, you get that expression. So number of possible message bits is 2 power k. Each message produces one unique code word and the total unique code word is 2 power k. So next comes the parity check matrix, that is H. H is given by IN minus k into PT. This is how you represent the matrix, where IK is the identity matrix of the size N minus k into N minus k. And PT is the transpose of the parity matrix that is being given in the question. So next is G. It is the generator matrix. Generator matrix is P into IK. This is how we represent the matrix. So on combining these two, how can we write H into G transpose? G transpose means this horizontal will turn into vertical. Okay, so here actually this is transpose. So next, what happens? You multiply this along with this. So you get it as P transpose into P transpose plus P transpose using the modulo 2 arithmetic addition. So hence H into G transpose is 0. Generator matrix creates a valid parity check matrix and test whether the code vector is valid code word. So now for any valid code word, it has to be C into H transpose should be 0. So you can say that there is no error in that system. So this is the parity checking equation. If it is not equal to 0, then you can say some error is detected. In a noisy channel, you can represent it as R is equal to C plus C, where R will be my received vector and C will be my transmitted code word and E will be my error vector. Now for each of the position of I, you can represent the error as EI like that. Next comes the syndrome. So syndrome, before going to the syndrome, we'll look into some of the problems related to the matrix and we will come back. So for a systematic 6,3 linear block code, the parity check is given, parity matrix is given as this. You need to find all the possible code vectors. This is the question that has been asked. So for this, what you have to do here is, first write down 6,3. What is that? It is n comma k. So our n value is 6 and k value is 3. So write down it is 2 power 3, that is 8. Okay, now C is equal to what? These are the two expressions that you need to know in order to write the matrix. One is C is equal to code vector that what we are generating. It is the D into the generator matrix. And then what? Then how to find out this generator matrix? It is given by IK, that is identity matrix into parity matrix. So now let's find out the first one, that is G. G is what? Identity matrix. So hashtag here it is IK. IK means it is I3 is to parity matrix that is being given. So IK means, as in the identity matrix, the diagonal will be 1 and the other will be 0, and the parity matrix has given in the question. Now you need to find the codes. So codes, I represented them as D1, D2, D3 like that. So this is the generator matrix that I have got. Now put it into the equation. C is equal to D into G. D into G means how much D code words that I have to find here is 8. So it is from D1 to D8 and this generator matrix I copy here. So now how do you find out the equations here? So basically what you have to do here is matrix multiplication. So D1 is multiplied with 1 and 0 and 0. So this is how you multiply it here. And then D2 to here and D3 to here and D4 to this line and D5 to this line, D6 to this line, like that you have to multiply. So once you multiply it like that, what you get there is, so you get that as D1 because other two are 0, so you get it as D1 and D2. This is my C0, this is my C1, this is my C2 and this is my C3, and this is my C4 and this is my C5. So this is how you write it. Just a minute. Okay. Next, message vector. So as it is, we need to have 8 to power 3 is 8. You need to write 8 message code words. So as usual, when you write this is 0, this is 1, this is 2, 3, 4, 5, 6, 7. Write it in the binary form. And next in the code word name, yeah, they have mentioned this as CA, CB, CD, C3. I have done it as C, not C1, C2, C3, C4. So here in the first 4 things, you just have to copy the same thing that you had written here. So here what you have to do is, what is the D0? D0 is what, I mean D1 is what here, 0, so that comes here. D2 is 0, D3 is 0. Then what is D1 plus D2? These two you have to add and write it here. D2, D3, you have to add these two and write it here. And then D2, D1 plus D2, you have to add this and this and write it here. You have to add using the modular 2 arithmetic addition. So similarly, in the same way for all these, you need to use these 3 as D1, D2, D3 and do next for this. So similarly, copy all using all this message vectors. You have to decode them here and write the code vectors. So take any 2 code words so to check whether you have done correctly or not. Let us consider just an example. Let's consider these two, CC and CD, and we will do the modular addition. Then what we get is, we get the CB as our answer. So this says that we have done the coding correctly. So this does not consider, you should not consider any carry in the modular addition. So that completes that. Now let's do one more question. Here the systematic 7,4 linear block code whose generator matrix is given. This is also one more question where we can solve. Next, here in the parity matrix, how parity matrix, I have explained this already. This is C into digit. This is the one formula that you have to know. Okay, now this is another one. You have to draw an encoding circuit for 6,3 linear block of code. 6,3 means N is 6 and K is 3, so it is again having 8 data code that we have to have. C1 is similarly what the last one we have did. The same way you have to write that table and substitute matrix, and you have to find out the C2, C3, C4, C5, C6. And now to design the encoder circuit, we require 3 shift registers and 2 modular registers and 6 segment. So how do you design it? You need to first place the 3 modular 2 adders and place the 3 bit shift registers. These are the 3 bit shift register. So from using this equation, you have to write the circuit. Like D1 is given as what? C1 is what? Only the D1. So first D1 only goes to the C1. So 1 completed. Second D2 goes to C2. Third completed. And for D3 it is C3. So these are the 3 channels that gets completed. Now we'll go to the C4. What is C4 given by D1 plus D2? This is the we have to use using the adder. So D1 along with the D3. Here you need to place one adder and add it modular to adder, and thus we get the C4. Similarly for the C5 it is D2 and D3, and for C6 it is D1 and D2. This is how you write the encoder circuit. So next, if the C is valid vector, then you have to prove that H transpose is equal to C into H transpose is equal to 0. First write the generator matrix and the parity matrix. So identity matrix you write, and then the parity matrix. So this gives our GI, then H. So finally what you have to prove, C into H transpose is 0. So for that you substitute that, and finally you can see G into H transpose is 0. Multiply on both the sides with the D. Hence you get it as D vector. So hence you get it as D into G is equal to C. Finally substitute this as C and you get it. Now coming to the next important topic, that is syndrome and its properties. Syndrome basically it is represented as S is equal to R into H transpose. What is S? It's syndrome vector. First thing it is this is the first thing that is computed in the decoding part. So size of the syndrome is given by 1 into N minus K, that is N minus K only. Now, how does this occur is in the message vector, you give the M as input. In the generator matrix, the encoding takes place and you get the code vector. This code vector is now sent to the parity check matrix using the way the decoding occurs, and you get the null vector as 0. So for the explanation part, you can refer this. Here you need to consider the C. Just write it in terms of N, C, R, and E, and finally the expression. So this is how you have to explain it. So syndrome, another thing is you can even write it as R is can be represented as C plus E, and S is equal to C plus E into H transpose. And this, as we know, this is equal to 0, and S is equal to E into H transpose. This is all where we use in deriving the properties. See here, first property is syndrome depends only on the error pattern and not on the transmitted code word. For that we have to substitute, as I said, and this will become the 0, and hence we get it. So next is syndrome for the multiple errors. If the error occurs at the position I and J, then you can say I 0, 1i, 1j, and 0. Then it will become S is equal to H into J, with these are the rows of the H transpose. Therefore, the sum of the rows corresponding to the error location is syndrome. Next is property 2, that is Coset. You can say here all the errors patterns that differ by a code word have the same syndrome. Defined like EI is equal to E plus CI. So EI H transpose is equal to E H transpose by multiplying H transpose on both the sides. Now each syndrome corresponds to the one coset. Total cosets is equal to 2 power n minus k. So decoder chooses mostly likely error pattern from the coset, that is CIH transpose 0 using the parity check equation. Hence we get it as EIH transpose is equal to EH transpose. It does not depend on the code word. Code word sent depends only on the cosets. Every coset has one unique syndrome. Now coset is nothing but it is a set of vectors. Exactly the cosets has 2 power k vectors, and total number of cosets is 2 power n minus k. Syndrome expression is given as like this has shown. Here each bit is a linear combination of error bits. Syndrome contains information about the error locations. So syndrome Without syndrome, 2 power n possible error patterns. With syndrome, it is only 2 power k possible error patterns. Before going to the minimum distance consideration, we will look into some of the questions. So here consider a 7,4k block of code with a parity matrix given. First question is to find the generator matrix and the parity check matrix G and H. And these are received an error we have received is R1, R2 and R3. This is an important problem. You can expect this in the exam. Determine it was an error during the transmission, or also detect and you have to correct the error. This is so simple if you understand. One is 7,4, it is n comma k, n is 7 and k is 4, it is 2 power 4. So we have to have 16 data bits. So here C is equal to D into G. For first we need G. So G is I into K. Identity matrix of K is 4 and parity matrix has given. And next here H is given by P transpose into In minus K. So we need to transpose the P. So H is given by P transpose. This matrix is transpose. Transpose is nothing but changing the rows and columns. So here this, consider this column, that is row here. This middle column is middle row, and this last column is the last row. Similarly, and this is H is given by I into n minus k. So similarly put the matrix here. What I is equal to 7 minus 4, that is 3. So you found the H matrix here. So to G and H are done. Now second part is R is given. So here the first equation what you have to do is S is equal to R into H transpose. The R that has been given and the matrix that we had found here, that is H, that has to get transposed like this. Transpose it like this. And once you've done this, you have to multiply it. Like multiply this whole column with this one first column, then this row with the second column, and this row with the third column. So you will get S1 bit. So finally on adding all those and simplifying, you got it as 101. What you have to do is you have to find out this 101 in the H transpose where it is. So you can observe it is in the second row of our matrix. So the where is the error? Then the error is in the second bit. So what happens here is there is an error. So in the second row, now you have to change the second bit in that part where the error is being occurred. So that we will do in the correcting code. So correcting code is here the matrix has in the second row of the H transpose. So the bit received in the second bit as error and it has to be corrected as C1 is equal to complete, it is 0, 0, 0. Because you can observe here it is the second bit was 1. So you can also write it as one more form you can write as E is equal to, you change it as what here the error is in the second bit, right? So you need to change it as 1 0 1 1 1 1 1. Correct. So here this is my S and this is my E. Finally, to find out C, what you have to do is you have to add R plus E. So adding R plus E is what? What is R? 0, 1, 1, 2, 3, 4, 5. Along with this, you need to add this. That is 1, 0, 1, 1, 1, 1, 1. So if you add these two, you will get this as answer. So this is how you have to correct the code vector. So second error is given as, here this is given as second error, same thing using the H transpose matrix multiplication. In matrix multiplication, I got it as 1, 1, 1. And here 1, 1, 1 is has to get changed in the this bit. So here it is in the fourth bit. So fourth bit it gets flipped as 1. So that gets corrected. Similarly, you can observe the R3 is given as like this and same multiplication and finally 0, 1, 0. It is in this bit. So the last but one bit has to get changed. So this has to get 1. It is our answer. So next another question is 6, 3 is given as a linear block code. Now generator matrix is, they have given the generator matrix itself. You have to find the H parity matrix and R1 and R2 is given. You have to determine the code word. So firstly, as I said, parity matrix is given by P transpose into In minus K. P transpose. So we know G is equal to Ik into P. So this is our parity matrix. This gets transposed here and In minus K. In minus K is 2 power here 3 is 8. So we need to find 8 code words. So R1 is given by the error and the transpose of this H transpose, and then we get the bit on simply matrix multiplication of these two. What do you get it as? 0 0 0. So where is the 0 0 0? There is not, it is not found in any of this, so hence we can say it is not having any error. Similarly, R2 is given, you just multiply, you got 0 0 1, that is in the last bit, so the last bit gets flipped up. Next is syndrome calculation circuit. Here you can observe S is equal to R into H transpose. This is where you represent in terms of N. Yes, okay. So here while representing it, how do you write it here is, first you will write the received bits here as Rn, R1 to Rn, that is being given, and finally you will represent it as S1 to Sn. In the middle you are having the parity matrix to represent it. Next is given matrix, construct the syndrome circuit. This is a different type of question where the received vector is, this is the received vector, and the parity matrix is given. Firstly, H is given as what? P transpose into In minus K. P transpose this matrix, and then In minus K, what is N minus K? Here it is not given, but you can write based on this itself. It is 3 cross 3, so this will also be 3 cross 3. And finally the H transpose of it. The error that is being given is what they have given in terms of R, and now the H transpose you're going to write it here. Now you have to multiply the each row with the each column like this, and then like this, and then like this. So based on that, for this column it is S1, and this column is S2, and this column is S3. So based on that, you get these three equations. To construct the syndrome circuit, we need 6-bit registers to hold the received vector 3 modulo 2 adders. So what happens here is, while representing it, what you have to write is, you have to construct the syndrome circuit. For that, you write the shift registers like this. And based on this equation, so what is S1? S1 is an addition of R1, R3, R4. So R1, R3, and R4, you add it and represent it as S1. Similarly, S2 and S3. So the next question is 7, 4, and here linear block code of the parity matrix is given. You need to find all the possible valid code vectors, encoding circuit, and error. RA is given, RB is given, RC is given. You have to draw the syndrome calculation circuit. So in this question covers everything, and this is super important. So C is equal to what? Firstly, D into G. So we need G. For G, you have to need IK into P. So IK into parity matrix. Substitute it, you will get the C vector. And from that, you have to give all the D equations based on that. So here we are having C1, C2, C3, C4, C5, C6, C7, and C8. So C till C8. Based on that, you have to write this table. And from that, as usual, as I said, combining the equations, you need to draw this circuit from RA, find out the error and change the corrected code vector. Then RB, find the error and change the corrected code vector. This is how. And lastly, you have to draw the syndrome circuit. So for the syndrome circuit, you need to know R and S. So R, you need to calculate the R from the matrix.